Okay, so hopefully you've had a go at all of these things first. So find the expression for divide dx. So here's our implicit differentiation, isn't it? So equals, so derivative of the first is 2 times the second plus the derivative of the second, which is dy dx, times the first, minus derivative of 9y squared is 18y times dy dx. Derivative of 9 is 0 is equal to 0. So what does that mean? We'll get dy dx outside of 2x minus 18y is equal to negative 2y. So then dy dx is equal to, let's take I reckon that negative 2 out the front if you like. Take a negative 2 out the front there and we'll go 9 minus 9y minus x. Cross all of them out. So y over 9y minus x. When y is equal to 1, okay, so at y equal to 1, what does that mean on the expression? You get 2x minus 9 plus 9 equals 0. So we get x is equal to 0. So we're talking about the point 0, 1. If I put 0, 1 into the derivative, dy dx is equal to 1 over 9. Okay, number 2, similar sort of question. Okay, so differentiate each term as we go. So the derivative of x cubed is 3x squared. Derivative of 2x squared y is the derivative of the first, which is minus 4x times the second, plus the derivative of the second, which is dy dx, times the first, plus derivative of y squared, derivative of y squared with respect to y. So we get 4y times dy dx, which is equal to 0. Dy dx outside of 4y minus 2x squared is equal to 4xy minus 3x squared. Dy dx is equal to 4xy minus 3x squared on. So hopefully this part of it's all okay. And we're going to put the point 2, 3 in. So dy dx will equal 2, 3. So we'll get 4 times 2 times 3 minus 3 times x, which was 2, over 4 times 3 minus 2 times x squared, which I'll just put 4. 624 minus 12 over 12 minus 8, which is 12 over 4, which is equal to 3. So of course then continuing, I'll just come here. So the gradient of the line is 3, so I get y equal to 3x plus c. Put the point 2, 3 in, we'll get 3 is equal to 3 times 2 plus c. c is equal to negative 3. Therefore the equation of the tangent is equal to 3x minus 3. Okay. Let's see. Given the relation, blah, 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 find the gradient of the normal to the graph of the relation at the point in the first quadrant where x equals 1. Okay, so first things first, dy dx is equal to 6x plus derivative of the first, so we'll go 2y plus dy dx times 2x plus 2y. Hopefully you're sort of getting a feel for, oops, that dy dx doesn't belong out the front, does it? just have it. So let's get dy dx outside of what? 2x plus 2y equals, I'll just do that, negative 6x plus 2y. Dy dx is equal to, take a negative 2 out the front, we'll get 3x plus y over 2x plus y. So the gradient of the normal at x equal to 1. So x equal to 1, we've got to find a corresponding y value. So if x is equal to 1, I'll get 3 plus 2y plus y squared is equal to 11. Y squared plus 2y minus 8 equals 0. Y plus 4y minus 2. So we get y is equal to 2 or negative 4. Now, since we're in the first quadrant, it's this point here I'm interested in, isn't it? So dy dx is equal to, at the point 1, 2, dy dx is equal to, so we've got negative outside of, what have we got, the point 1, 2, so we get 3 plus 2 over 1 plus 2, which is equal to negative 5 on 3. So therefore the gradient of the normal will be equal to the negative of that reciprocal, which is 3 on 5. Alright, so the equation of, we've got f double dashed of x. So look, technically maybe we're not quite ready for this, but I think you'll probably give it a go. So obviously we've got the second derivative here and we ought to get back to the first derivative. So we need the antiderivative of negative sec squared 2x dx. So we haven't technically done the integration of that yet, but we do know the derivative of tan ax is sec squared x, or a sec squared x. So we're going to end up with the antiderivative of this is going to be equal to negative 1/2 tan 2x plus some constant c. So f dashed of x will equal that. So what's our point? It passes through the point and has a gradient of negative 1 at that point. So at x equal to pi on 8, f dashed of x is equal to negative 1. So if we put negative 1 is equal to negative 1/2 tan of 2 times pi on 8, which is pi on 4, plus c. Tan of pi on 4 is 1. So c will equal negative 1/2, won't it? So I've got f dashed of x will equal, f dashed of x will equal minus 1/2 tan 2x minus 1/2. We want the gradient of the curve at pi on 12. So f dashed of pi on 12 is equal to negative 1/2. Tan of 2 times pi on 12 is pi on 6, which is minus 1/2. Tan of pi on 6 is 1 on root 3, so we'll go with root 3 on 3, minus 1/2. Therefore, the gradient, so we'll put gradient is equal to, so if we take negative 1/2 at the front, we'll get a root 3 on 3 minus 1. Negative 1/2 at the front, we'll go with root 3 on 3 minus, look, we could leave it like that. So we'll go with minus 1/6 outside of, oh, hang on, it's a plus there. Root 3 plus 3. Okay? All right, another implicit one it looks like. Family occurs defined by blah, 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 blah. Okay, is now on a bar. Verify that every curve in the family passes through the point 0, 4. Okay, so let's substitute the point 0, 4 in. And I'm assuming it will be true. So x is 0, y is 4. We get x is 0, I get 0 minus 4 squared plus 0 plus 5 times 4 minus 0 equal to 4. So we get negative 16 plus 20 equals 4, which is true. So that's fine. And find the other point of intersection with the y-axis. So y-axis implies x is equal to 0. So at x equal to 0, we get negative y squared plus 5y equals 4. So I'll get y squared minus 5y plus 4 is equal to 0. Y minus 4, y minus 1 is equal to 0. Y is equal to 4 and 1. Therefore, the other point of intersection. So the other point of intersection is the point 0, 1. Okay. Find an expression for dy dx. Always the way, isn't it? It's on a different page. So I brought that function across. So I differentiate everything. So with respect to x, I get 9x squared minus 2y dy dx. Derivative of kx is plus k. Derivative of 5y with respect to x is 5 times dy dx. Got a chain rule here, so the derivative of the first term is negative 2 times y plus derivative of the second term, which is just dy dx, times the first term, which is negative 2x, equals 0. So let's get dy dx outside of. Is there a positive term there? There's a 5. So I'll fill out with a 5 minus 2y minus 2x is equal to 2y minus k minus 9x squared. So dy dx is equal to, divide that whole thing by that bracket, 2x. Okay, might try and simplify that too much. Hence evaluate the gradient of the curve at the point 1, 1. At 1, 1, dy dx is equal to 2 minus k minus 9 over 5 minus 2 minus 2. So that's 1 on the bottom, which is just 2 minus 9, negative 7 minus k. That'll do us. Now it doesn't say anything about leaving the gradient in terms of k, so there must be a way of solving for k. So we've got a point the curve goes through is 1, 1. So if I substitute the point 1, 1 into the expression, I'll get 3 minus 1 plus kx, which is k, plus 5 minus 2 has to equal 4. So what does that give me? So k will equal 3 minus 1 is 2, plus 5 is 7, minus 2 is 5. Take that across. K is negative 1, I reckon. Therefore, we get dy dx is equal to negative 7 minus negative 1, which is negative 6. Hence evaluate the gradient of the curve. So maybe we should put therefore gradient equals negative 6. Alright, find all real values of m such that y is a solution to that dE. Okay, so y dashed is equal to, or maybe we should use their notation. So let's go with dy dx is equal to me to the mx, d squared y dx squared is equal to m squared e to the mx. Any other terms we need? No. So therefore we get d squared y dx, so we get m squared e to the mx minus 3 me to the mx minus 10y, which is 10e to the mx, equal to 0. So if I take e to the mx out the front, I'm going to get m squared minus 3m minus 10 is equal to 0, which implies then we get e to the mx outside of negative 5 plus 2. Now, since our exponential function does not equal 0, m must equal positive 5 and negative 2. Okay, so let's have a look. We've got sine inverse, r sine inverse of a half x plus 1. So, all right, let's have a quick, what's my sine inverse graph look like? It looks a bit like that, doesn't it? And so that's negative 1 to 1, and that's pi on 2 to minus pi on 2, isn't it? So, first things first, domain. So negative 1 is less than or equal to a half x plus 1, which is less than or equal to 1. So subtract 1, so we get negative 2 less than or equal to a half x less than or equal to 0. Multiply by 2, we get negative 4 is less than x, which is less than 0. So my domain is from negative 4 to 0. What about my range? So let's think about this first. So inside the bracket doesn't affect my range. The 2 on pi at the front multiplies. So my range at the moment, range is from negative pi on 2 to pi on 2. I'm then going to multiply everything by 2 on pi. So then it becomes from negative 1 to 1. And then I'm going to subtract 3, so it becomes from negative 4 to negative 2 is my range. Okay, given, find f dash of x of your answer. So let's have a look. So u equal to a half x plus 1. So then the derivative of 2 on pi sine inverse of u is equal to, so f dashed of u is equal to 2 on pi times, what is it? It's 1 over of 1 minus u squared, and du dx is equal to a half. So the half, so we're going to end up with 1 on pi outside of 1 over the square root of 1 minus u squared. I'm going to write that as a half x plus 2 all squared. Yeah. So let's just concentrate on that expansion first. Yeah. So let's have a look at 1 minus, so that's going to be a quarter of x squared plus 4x plus 4. That's all under a square root sign. What do I want to do there? I could take that 4. Well, let's go 1 minus a quarter x squared minus x minus 1. So the 1's cancel, which leaves me, I'm going to bring that quarter back out, and I'm going to write that as x squared minus 4x. So that's what's under the square root sign. So therefore, f dashed of x is equal to, so we've got 1 on pi, 1 over the square root of minus 1 quarter of x squared minus 4x. That looks about right. 1 on pi times, so that quarter in there, so let's take the square root of a quarter is a half. So let's go a half outside of We'll take an x out the front. That's a plus 4x in there. X out the front. So what if we leave the negative x plus 4, which equals 1.5 is 2 over pi negative x. Yeah, doesn't matter about the negative sign. It could be in or it could be out. But just to, there's my negative sign x plus 4 there. Negative sign, there should be a plus there, shouldn't it? If I take a negative out the front. Yeah, so that was lucky. Lucky I know probably which answer I'm looking for. So 2 on pi, negative x plus 4. Not bad. All right, got f of x, find f double dashed of pi on 2. So what's f dashed of x? So what is the derivative of tan inverse of a, or tan inverse of x is a over, we've got that formula sheet there, haven't we? So the derivative of tan inverse of x is 1 over 1 plus x squared, so tan inverse of x on a. So if I put u equal to x, I get tan inverse of u, so I get 1 over 1 plus u squared times du dx, which is 2. So we end up with 2 over 1 plus 2x, which is 4x squared. So that's okay, so that's f dashed of x. F double dashed of x is equal to, derivative of the top is 0 times the bottom, minus derivative of the bottom, which is 8x over, derivative of the bottom times the top over the bottom squared, which is negative 16x over 1 plus 4x squared. So from there, we're just going to substitute in our pi on 2, which is a bit messy really, isn't it? So we get negative 16 times pi on 2 over 1 plus 4 times pi on 2 squared, all squared, which is negative 8 pi over, pi on 2 squared is pi squared on 4 times 4, so I just get a 1 plus pi squared, all squared. That doesn't look too bad.